So welcome back to another video. So we're actually discussing this Bayer villager oxidation or rearrangement. So this is an important application of acids in the oxidations. So in this reactions or rearrangement, it is an oxidative rearrangement of ketones into esters by using paracids. Example: peracetic acid, perbenzoic acid, or we can use metachloroperbenzoic acid. In short form, it's called as a metachloroperbenzoic acid, and so on. So what we can do is we can convert here a ketones into esters by using this peracetic acid or perbenzoic acid or metachloroperbenzoic acid. So we can take an example, or it's a general example, CO R dash. Here R and R dash are not equal, they are different, not identical. So we are using some paracids. So here the oxygen will be inserted either here or here. There are two possibilities. The possibility depends upon the electron rich group. Here, if R is more electron rich than R dash, it's more electron rich. R is more electron rich than R dash, then the oxygen will be enters in between R and CO. So you will get R O C double bond R dash. So here we already know that this paracids oxygen rich compound, they are electron deficient compounds. Electron deficient needs electron rich group. So that is why any electron rich group migrates preferentially to the oxygen. So here we can take another example, is that CH3 CO C2H5. So in this case we can use some trifluoroperacetic acid. So here the methyl and ethyl. So on comparison of methyl, ethyl is more electron rich. So therefore the oxygen will be enters here. Oxygen will be enters in between CO and C2H5. So we will get CH3 CO O C2H5. Now the mechanism of this reaction, can take a general example, R dash, and we are using any acids. We can take any acid, some trifluoro. There are three oxygen connected. This is an acid per acid. The job of an acid is to protonate. So this acid actually ionizes minus plus H plus, and here we have a lone pair of electron. So this lone pair of electron takes this H plus and protonated. The carbonyl group is actually protonated. Now the protonated carbonyl group contain a positive charge, then R dash. Now this pi electron shifted to positive charge. It is in the resonance. RCOH. This is R dash. So here we have a positive charge will be created onto the carbon atom. Now we have the conjugate base RCOH. So here it is a positive, here it is R dash. Now we have O, C double bond O, CF3, O minus. Now the minus, the electron rich attacks on the electron deficient. So we will get R, C, OH, R dash, O, C double bond, CF3. Now in the next step we will get a rearrangement process. We have the lone pair of electron actually makes a bond. This is the driving force for the rearrangement. And now the electron rich group, we already said that R is more electron rich for the convenience. If R is more electron rich than R group, this group migrates to oxygen. So this is an electron deficient oxygen. Electron rich migrates to electron deficient oxygen. Once it migrates, this bond breaks up. Get this bond migrates, the bonded electron attached to oxygen, you will get a negative charge. So we will get R, O, C double bond OH plus R dash. Now what is left out is actually CF3 CO O minus. So this is minus, will take up H plus, neutralize the positive charge. So you will get R, O, C double bond O, R dash. So this is an ester. Now the electron rich group always migrates to the electron deficient oxygen during the rearrangement. So we can make a note. The electron rich group always migrates electron deficient oxygen center during rearrangement. Now the electron rich, the order of migrations or priority of migrations or migratory aptitude is as follows. First is actually tertiary alkyl group, then phenyl group or aryl, which is equivalent to secondary alkyl, then primary alkyl, then methyl group. So this is the migratory aptitude. If we take another example, an acetophenone CH3. So if we use any acid for acetic acid, so here what will happen is that, so we need to find out which is more electron rich. So compared to phenyl and methane, so phenyl is more electron rich. So the phenyl group is actually migrates, we can write. So the phenyl group, electron rich group, which is a phenyl, will actually migrates to electron deficient center. So it migrates to electron deficient center. So you will get oxygen in between pH and CO at CH3. Another example, so we can make here. pH, trifluoroperasitic acid. Now either the pH or this group. This is a tertiary alkyl group. So this is tertiary alkyl group. We know that tertiary alkyl has more migratory aptitude than phenyl group. So therefore the oxygen will be inserted in between the carbonyl group and the tertiary alkyl group. So you will get the product OPH. So this is a product. We'll take another example. CH3CO CH3. So it is a alpha diketone. It's a diketone. You can use metachloroperbenzoic acid. Now here it is identical. So it's identical. So therefore the oxygen will be attached here in between two carbonyl group. CH3 CO CH3. So you will get an acetic anhydride. Can make a lot of example we can make. Now so with respect to stereochemistry, so during the rearrangement process, this rearrangement, so if you take pH CH3 H C double bond O CH3, so this is actually, this is 1, this is 2, this is 3, this is 4 with respect to RS notation. So therefore you will get the anti-clockwise direction. So therefore S, this is 1 2 3, so S 3 phenyl 2 1 2 3 4 butanone. Use peracetic acid. Now during the course of the rearrangement, the stereochemistry of the reactant molecule will be retained. So compared to methyl group, this group is more electron rich. It contains phenyl group as well as CH3 group. So therefore that group, this group actually migrates to the electron deficient oxygen with the retention of stereochemistry. The stereochemistry is retained during the course of the rearrangement. That actually suggested that the rearrangement is this evidence. The rearrangement is actually intramolecular. Intramolecular rearrangement. So if it is changes the stereochemistry, then we can say that it is intermolecular. Now the migratory aptitude will never indicates that intramolecular means the migratory aptitude never detach from the substrate. That indicates it's a intramolecular rearrangement. It not during the course of the rearrangement, the migratory aptitude will never detach from the rest of the molecules. That is why it's called as an intramolecular rearrangement. So another evidence we can take is actually crossover experiment.